I want to take a look at one more function where a limit is undefined, but unlike the other functions we looked at in class, this one doesn't even have a left or right-handed limit. This is an example of how things can go very wrong. So what we're going to do is we're going to make a table of values like we usually would. We want to know the limit as x approaches 0. So let's put an x there and then sine of pi over x here. And we want x to get closer to 0. So let's look at 1 and maybe 1/2 and maybe 1/10 and maybe 1/100th. We could write these as decimals, but I'm writing them as fractions because I think it'll make the math a little bit easier. Now, if we plug in 1, then we've got sine of pi over 1, which is sine of pi. And if you'll recall, sine of pi is equal to 0. So that is 0. Now, if we do 1/2, that's going to be sine of pi over 1/2. And we know that dividing by 1/2 is the same as multiplying by 2. So this is sine of 2 pi. And that also happens to be 0. Interesting. If we do 1/10, this is going to be sine of pi over 1/10, which is the same as sine of 10 pi. And that's also 0. And we're going to see anytime we have 1 over an integer, we end up having it be sine of that integer times pi, and that's always going to be 0. So it almost looks like the limit is going to be 0, at least the right-handed limit, because we've picked some positive numbers here. But let's actually look at what the graph looks like. Now, here is a digital copy of the graph. I'm not doing this by hand because it's quite a complicated graph. The fact that there's an x in the denominator inside of the sign ends up causing some pretty wild behavior here. And it looks like this is just a blob, but what is happening to the function as we go from the right? It looks like the sine function, as in it is oscillating between -1 and +1. But as we move closer to 0, that x in the denominator causes us to oscillate more and more frequently. And it looks like this is just a solid patch of color here, but the reason it looks like that is because it's oscillating so frequently that the width of this curve, I mean, obviously a curve has no width in real life because a point has no width, but when it's drawn on a program, on a graphing calculator, it has to have some width. And we get to the point where the width that the curve is drawn as is bigger than the distance between each oscillation. And so you can't actually tell between them. And it is actually it is oscillating up and down an infinite number of times in this gap. That's what's happening. Whenever we have an integer value of x, a fractional value of x where it's 1 over an integer, like 1/2, which is 0.5, or 1/3, which is 0.333 repeating, or 1/4, which is 0.25, or 1/5, which is 0.2, or 1/6, or 1/7, or 1/8, or 1/9. Anytime we have 1 over an integer, it goes back to 0. And we know that there are an infinite number of fractions in the form 1 over an integer between 0 and 1, right? 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7, 1 over 8, 1 over 9, 1 over 10, etc., 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 infinitely many. And so this oscillates back and forth an infinite number of times. So these zeros that we have come from the fact that our function does hit 0 an infinite number of times. However, it also hits 1 an infinite number of times, and it hits -1 an infinite number of times. And so Despite this table of values that happens to, by complete chance, hit the zeros over and over again, and it looks like it's just staying at 0, this function is not staying at 0. It is moving back and forth an infinite number of times between -1 and 1. And so because there's not a single number that it's always getting closer to when it's approaching 0, that means that the limit does not exist. And not just the two-sided limit doesn't exist, but the left and right side limits don't exist, because you can see on the left and the right side, it continues to oscillate between -1 and 1 again and again. It is a complicated function, and the graph is complicated, and it is a really great example of a function where a particular limit doesn't exist. But at the same time, it's a relatively simple function. We don't need an equation with 37 parts. This is just sine of pi over x, right? There's not that much to it, but even though it is relatively simple, we've got some crazy behavior around x equals 0. And the point is, there's actually 2 points. One, there are many situations where a limit might not exist, even with simple functions, so we do have to be careful. And 2, it is possible to pick a few values for x, see a pattern, and think that that means that a limit exists when you just happened to pick values that made it seem like something was happening when that's not the whole picture. So this is why we make tables of values with lots of numbers. Sometimes we try and pick numbers that aren't particularly nice in our tables of values, just to make sure we don't have this sort of a situation going on where we happen to be picking the ones where there are zeros. I want you to understand that limits can be quite complicated, and if we don't really take time to thoroughly look at them and try to understand them as best as we can, we might fall into some pitfalls and accidentally make a wrong conclusion. This is why we spend a few weeks on limits in calculus, because we really want to look at different examples and really understand what's going on.